All right. Good morning, everyone, and welcome to today's webinar on understanding the current landscape for evaluating pulse quality. So my name is Janelle Carlin. I'm the Director of Quality and Processing at Pulse Canada, and happy to have you here today to talk about methodology. So I am joined here by three experts in the Canadian research ecosystem. We have Dr. Jim House with the University of Manitoba, Dr. Ning Wang with the Canadian Grain Commission, and Dr. Mike Nickerson with the University of Saskatchewan that are joining me here today. So before we begin here, I just want to take some time to talk about a couple of housekeeping items. So if you have any questions, we will be doing a question and answer period with all three of our experts here at the end of the webinar. You can submit your questions through the comments and the chat function, which is located on the right-hand side of the screen. And we will be recording the webinar for today and circulating that to all those who registered. So that will be available after the fact. And we do have a survey that we are hoping to get some of the participants here to fill out. And I will be providing a little bit more context as to what that survey encompasses here right away. So just before we begin, I'm just going to be providing a little bit of a background and introduction to today's webinar here on understanding the current landscape when it comes to evaluating pulse quality. So one thing that we are seeing, I'd say, especially in the past 5 years or so, is an increase in terms of the innovation and utilization of pulse ingredients. So this slide here just represents an example focused in on pea protein, where it used to be more of a novel ingredient. We've had production in Canada since the 1980s, but only up until recently have we really started to see growing adoption and it becoming a very prominent ingredient source in global food innovations here. So this slide here highlights the number of global new product launches by top plant protein sources. So it gives you an idea. It doesn't show necessarily demand and volume, but it gives you an idea of innovation and utilization of these types of ingredients here. And you can see that pea protein is really emerging as the third most common plant protein source in some of these new and innovative product launches. And what we're seeing as a result as well is that multiple suppliers of pulse ingredients are constantly emerging there. So I mentioned we have had processing here in Canada since the 1980s, but recently, especially since around 2015, there are a number of new companies that are coming to market, offering a variety of different ingredient sources. And it's becoming increasingly important then to be able to distinguish between these suppliers and also within suppliers that are offering multiple different ingredient options and really understanding which ingredient might be better suited for a particular application than another. So understanding quality then and really trying to pinpoint what ingredient, what supplier might be best suited for a particular application, it's becoming more important for our sector to really understand factors that are contributing to variability in that quality. So this slide here is highlighting a number of different attributes that might affect some of the quality characteristics of either that whole seed or the ingredients. So we see differences across pulse type, whether it's cultivar and genetics, the growing environment that crop was produced in, storage post-harvest, as well as storage of the ingredient itself, the processing technology that was used to produce that ingredient, as well as the conditions that are applied, as well as what that ingredient is and what are those really intrinsic characteristics of that ingredient. But one thing that we're here to talk about today a little bit more specifically is actually the analytical tools, the testing procedures, and conditions that are applied to actually get to that value that helps make that decision and helps us understand the quality of that ingredient. So one thing here, I just wanted to provide some context as to the current landscape is that we do see a lot of variability when it comes to pulse quality measurements in terms of the analytical procedures that are being used to really test and understand these ingredients. So here I have an example where we're looking at emulsification activity and stability. We're looking across the literature at all of the methods that are applied. It really boils down to a couple of key core references that were the ultimate source for a lot of those methods here. You can see those listed on the slide here today. But even though they are being developed from a lot of these key sources, we're still finding more than 24 assays emerging in literature with very distinct testing conditions. So there is a lot of variability just in terms of how we're seeing emulsification activity and stability being measured. And this slide highlights some of that variability where we do have a lot of very similar steps across the board. If you take a look at the literature that's being used to evaluate emulsion activity and stability. However, at every single step along the process, there are multiple different points and conditions that might be altered or changed from one reference to another that might have an influence there on that final value. And what this does is just by altering those analytical procedures and the conditions that are applied, is it might result in differences in that reported value, which makes it difficult to compare across literature for that particular analyte of interest there. So one thing that this does is that when we're looking to really understand some of those other factors that are affecting quality of pulse ingredients, is it's really difficult to compare across studies. So that may limit our ability to fully understand some of these extrinsic factors that are affecting pulse quality. So here I just have an example where we're looking at two different studies that are trying to understand the influence of milling and milling treatments on pulse functionality, pulse ingredient functionality. And you might not be able to directly compare the results between two different publications simply because those analytical procedures are not consistent across the studies. So one tool that is out there and that we can work towards for the industry is by standardizing pulse ingredient methodology or looking towards industry-aligned methods as an important tool to really be able to distinguish the performance of any individual ingredient from one another or from publications from one to another. And there are a number of organizations that are working towards this. However, with the context of the pulse ingredient landscape, we are limited just in terms of the methods that are available and standardized to evaluate quality. So today's agenda here, we're going to be talking about some methods in particular. So there's been some work under the Pulse Science Cluster that was funded by the Canadian pulse industry here in Canada that Dr. Ning and Dr. Nickerson were involved in, working towards foaming stability and capacity method development, oil absorption capacity, seed hardness, and pasting properties. So they're going to be presenting some of that work here today. And then we're also joined by Dr. Jim House, who's going to be talking about some in vitro methods for analyzing protein quality as well. But just before we begin here, I did want to highlight one program that has recently launched under Pulse Canada. It's called the Science and Technology Industry Program. This is a program that was formed for our members as a way for them to really help to prioritize and shape pre-competitive research in the Canadian pulse sector. And one of the areas of work that has been prioritized is this exact topic that we're here talking about today, developing industry standards and methods. And one of the points raised by this committee in particular is the fact that there might be differences in priorities that are emerging when you're looking at methods that are developed in the academic sector as well as for industry. So it's important to consider the needs for both, where academia is really focused on highly scientific and accurate methods, whereas on the industry side, we might need more simple and applicable methods that are quick and are able to use amounts that are reflective of the actual sample that you're working with. We also see differences just in terms of, on the industry side, the ingredient manufacturer themselves and the food and beverage manufacturers might also have differences just in terms of why they're looking to evaluate pulse ingredient quality, where on the processor side, it might be more meeting customer needs, being able to understand applications for their ingredient, and on the food and beverage side is being able to screen and identify that optimal ingredient for their particular food application. So because of that, the committee there that was referenced, the STIP committee has launched a survey where they're really trying to understand what's being done in the commercial sector. So ingredient manufacturers as well as food and beverage manufacturers. So this survey here, you'll see a link below your screen here today. And we'd really appreciate, as we're trying to really gain insights as to some of the challenges in terms of evaluating pulse ingredient quality that are occurring again on that commercial side. We do have some understanding on the academic side, and we'd really look forward to your feedback there to understand your needs more on that commercial setting. So with that, I'm going to pass things off to Dr. Mike Nickerson, and he's going to, I'll give it away to him. So thanks everyone.
Perfect. Thanks, Janelle, and thanks, Pulse Canada, for inviting me for this really nice workshop. Um, so today I want to talk about, foaming methods, right? Foams are extremely important, and proteins, especially, pulse proteins from pea or faba bean or chickpea or like, they all have a really functional role in creating foam-based products. So, oh, sorry. So, what are foams? Well, foams are basically mixtures of a liquid with gas bubbles dispersed in it, and within that liquid, there's proteins, and how the proteins align and interact within that liquid phase really helps stabilize these gas bubbles in your foam product, and we can create. As changes in the density of these gas bubbles occur in your product, you see a migration of gas upwards and a top layer of foam being formed in your product, and you get this polyhedral type honeycomb structure when you start looking at the structure of the foam. Now, as you know, foams are really important in a wide range of food products, and they give the creamy mouthfeel. So, whether it's an ice cream, you have nice eye appeal and bulk density, so we can create bubbles in bread, or create foams in beverages and coffee, or in whipped desserts, right? So developing these foams based on the proteins is really important avenue in terms of product development. So, how do foams form? So, I mentioned that, foams are in this liquid phase, and I just put an example of one pea protein, and we apply some shear. So we stir it or beat it really fast. And what that happens is the protein structure unravels and unfolds and exposes buried hydrophobic groups and hydrophilic. So they like to align at the oil water or the gas water interface and create a nice film around that gas bubble. And so if we look at within the interior of that gas bubble, these proteins form this network to stabilize the foam to get a nice thick surface that can go in the products such as coffee and other things. So proteins really act to resist destabilization of the gas bubbles in the foam. So, in industry, or a lot of the papers in academia use two types of things to analyze foam: a foaming capacity and a foaming stability test. And this really gives an estimate of how well your protein ingredient performs as an ingredient in a food product. So foaming capacity is the ability of a protein at a given concentration to generate a foam. And as Janelle mentioned in her emulsion activities example, a lot of different factors can affect this. So the variability among different labs and within lab can be substantial. So you have to be really conscious of how you're actually making these measurements. Now, foam stability is once you make that foam, how stable is it over time? Because there's separation that will occur, destabilization, and smaller drop bubbles emerge with bigger bubbles, and you get a breakdown in structure. So there are a number of factors that can influence. For the first case is foam volume. So how thick is your foam? And obviously protein type has a big impact. They all have different compositions and surface properties and sizes. So all these factors that are inherent to the protein structure can impact foaming. So maybe for protein from pea or another pea fraction or faba bean, they all have different foaming properties because the protein itself is different, and how we make that protein, fractionation and other things can impact things as well. When we talk about making products, a lot of them have different compositions or formulations: salt, fats, sucrose. All these can impact foam volume. Also, how much shear and what are some protein concentrations in that foam. Now, stability, that's related to the surface tension. So how well that protein aligns at that gas bubble interface to prevent separation, diffusion protein in and out, because it's a dynamic system, film strength, and bubble size. So the smaller the bubbles, the more stable the foam tends to be. So how do we measure this? So this is a really quick, dirty measurement, but it gives quite accurate estimates of how well a protein performs as a foaming agent. So, the first step is, let's create the solution that we're going to foam. So typically in our lab, we disperse about 1% of the pulse ingredient in water, and we adjust it at pH 7. Now, depending on the study that we want to do, maybe we look at different pHs, maybe we want to look at different concentrations depending on the final outcome. But we create a solution. So this is our standard solution, 1% at pH 7. And then we start preparing the foam. So we then take 15 mils of that dispersion and put it in a narrow vessel. So it's just a beaker. And we control the size of the beaker, because that's when we put the probe in, a certain amount of foam is generated in that volume. So if we chose a different beaker, we could get different shearing mechanisms that happening inside that liquid. So then we put the homogenizer probe just below the interface of the gas and water, and we find that's the greatest impact, because that's where we want the proteins to align at that interface. They help stabilize the air bubbles once they form. And then once we have that mixture, then we transfer that to a graduated cylinder, 50 or 100 mils, and record the volume to get the foam volume height. And then we watch that foam degrade over time. And typically in our lab, for standard measurements, we do 30 minutes, sometimes longer if it's a really good, strong foam, to see differences in conditions. So really, you have to standardize the method that you use in your lab, whether it's a company or academia, and really pay attention to values that you see in the literature, because they can vary quite a bit. You have to understand the method and tailor it to your situation. This is just an example of the calculation, but as you can see in the picture, that foam starts decreasing, and you see a buildup of that aqueous layer at the bottom. That helps calculate the foam capacity and stability. Now, these figures are just a really quick snapshot of commercial proteins, and I have P as an example, and right at the end. But compared to the eggs, soya, and others. So, we have to remember that different suppliers of proteins produce proteins differently, right? So some may be more thermally treated, others are more native. So depending on how we produce a protein, we can get vastly different results. So this is just a snapshot of one particular ingredient and how it compared to other ones on the market. In the lab, we can prepare pea that has really great foaming properties. So it's really dependent on how we make the ingredient, but then how do we measure that and quantify it? This is just an example of a study that we did comparing functionality of a legume and then cereal flours that I didn't show in this particular instance. But as you can see, they're all very similar. In fact, the foaming capacity of the pulses tends to be at or above soya, which is a dominant in the marketplace, at least for the flours. And, all very similar stability. So all these pulse ingredients are really great foaming agents, and they can be tailored to different product applications. Now, at the university, we also have advanced tools to understand the protein and how they align at the interface and structure of these foams and how it breaks down. So this is a new tool that we have in our group called the Dynamic Foam Analyzer, and it allows us to take or probe a greater in depth into understanding foam volume and stability and how it changes in response to our pulse protein. So this machine can look at the volume, but really look at the microstructure of that foam. And this is just a quick example. We're looking to modify the protein using a pH shifting approach. So we're just changing the structure of the protein, right? So we're unraveling, exposing more groups to try to enhance that functional property of the ingredient. But when we look at looking at the foam microstructure. So on the left, we have untreated pea protein isolate. On the right, we have a pH treated pea protein isolate. And going left to right, we can see an increase in foam volume. So we can enhance that foam capacity and the foam produced. The foams have larger bubble sizes. So this micrograph is the actual bubbles, and we can monitor changes in bubbles over time and get an idea of bubble growth and breakdown. Now, that modification improved the capacity, but lowered that stability aspect. So this is just some data below about how we can modify the properties of a protein by controlling structure to tailor or change the foaming properties of that ingredient. So some of the challenges of doing foaming tests, so we talk about the graduated cylinder test, which is the main one that we can perform in industry. A lot of different factors. So it's really important to standardize how you make your protein, where the protein's coming from, your equipment that you're using, everything from a beaker to the temperature to the homogenizer to the probe type. All these can impact the end results of those foaming tests. Duration, so different probes and even different homogenizers can give different levels of shear that's happening in your sample. So that can generate different types of foams. It can alter the protein structure in different ways. And the duration, so you do short versus long mechanical shear on your foams to generate these. So it somewhat depends on the ingredient that you're working with and the end use application, right? So pay attention to the equipment. Often I recommend the industry, develop a quality test for your lab, for your ingredient, and then, look at other ingredients on the market and how does you compare to using your tests that you develop in your lab, using your equipment to evaluate how your ingredient is performing for quality aspects. Because it is hard to compare in the literature. You can look at trends, but it's really hard to compare values across, whether it's a manuscript or actually industry reports about their ingredients, right? You have to understand what's being done, evaluate yourself, and understand this particular test. So that's it. If you have any questions, I guess we're going to do a question period at the end. And thank you very much. My email contact is there if you have any further questions afterwards.
Thank you so much. That was great. We'll take questions at the end, so just be sure to make a note of who your question is for when we do get there, but you can put them in now and we'll get to them later. Next up, we have Dr. Ning Wang with the Canadian Grain Commission, and I will pass it off to you. So thank you. You're on mute there, Ning. Might have to.
Thank you. Thank you, Janelle and the Pulse Canada for giving this opportunity to present some of the results. So yes, this morning I'm going to talk about the development of methods for assessing oil absorption capacity, pasting properties, and seed hardness for pulse material. So oil absorption capacity is determined by the maximum amount of oil that the material can take up and return within the matrix and the low centrifugation. It's usually determined, measured by mixing a sample with excess oil and a centrifuge, and then you determine how much oil is absorbed by the sample. So the methods, it's a very simple, straightforward. So, however, we observed other issues associated with those methods. So we found that less dense material drains off with the unabsorbed oil during the decanting, and some materials reabsorbed oil after centrifuge. So those issues can cause measurement error in those methods. Oh, sorry. So to address those issues, we developed the methods for measure oil absorption capacity by using filter paper to separate unabsorbed oil from a sample during the centrifugation. So this method was published in Serial Chemistry. So for more information or detail, you can refer to the paper. But today I will provide you with an overview about the method. So here is a list of the apparatus used in the methods. So it includes a test tube, filter paper, plastic syringe barrel. Here's the vortex, and also you need a centrifuge tube, centrifuge, and balances. So the method is pretty simple. So now I'm going to just briefly walk you through the steps to measure the oil absorption capacity. So first of all, you just cut a piece of filter paper in circular or square shape, and then you fold it and insert into this syringe barrel. And then you weigh a pulse sample in a test tube. So after that, you weigh the total weight of this syringe barrel, filter paper, and the tube with the sample. So you add oil into the test tube. So and then you vortex it, and then you leave it for a certain time, and then you the test tube inverted into the syringe barrel with the filter paper at the bottom of it, which is then you place this into the 50 ml conic centrifuge tube. So you centrifuge the sample for a certain time of at certain G force, and then you got so the oil you can see pass through the filter paper. So then you weigh the syringe assembly. Here you take out to weigh it, and then you calculate by subtract the weight of the syringe assembly before oil addition from the weight of the syringe assembly after centrifugation, and then you will get how much oil absorbed by the sample. So this method allows oil that's not absorbed to pass through the filter paper and collect at the bottom of the centrifuge tube, where remaining all solid material within the test tube. So the new method prevents the loss of sample material and minimize the reabsorption of oil by this material. Okay, so this table shows the comparison between the conventional methods and the new methods for measure for the oil absorption values of flour, protein concentrate, isolate, and the processed flour from pulses or soy materials, soybeans. So you can see the results. The result shows that the conventional methods produce or give a higher oil absorption capacity values than did the new methods. So I think which those could be that's due to the those issues that I talked before. So this method also we applied it to various flours and protein concentrate isolate from pulses and soybeans. So we determined the variability within the lab, reproducibility of the methods by three operator or technicians in our lab. So the results you can see here, you can see there's no significant difference between the operators. So you can see, I just give you example here, so you can see the rest as well. So which demonstrates that the result determined by the methods were reproducible. And also you can see this column, so shows variation of different pulse crops, pulse samples in oil absorption. You can see the methods produce good separation among the samples differing in oil absorption capacity. Okay, so yeah, the oil absorption method is very simple, straightforward. So like I mentioned, it's published. You can go get more information about the details about the methods. So now I would like to talk about the methods for determining pasting properties for pulse flours, I would say, for pulse flours. So a rapid viscosity analyzer, or we call the RVA, has been widely used for measuring the pasting characteristics of starch from cereals and the controlled temperature. So the picture on the left is an RVA instrument, and the right is a typical pasting curve for a material. This time, I think it shows you is from the pea flour. So all those parameters, such as peak viscosity, through breakdown, final viscosity, all these parameters can be determined with the user software provided by the together with the instrument. So when you go, however, when you go through with the literature, so you can find there are various different operating conditions were used. So there was no common method available for measure pulse flours. So due to differences in test condition or variation in the RVA procedures, so this has caused the difficulty in data comparison from different laboratories or studies. So therefore, there is a need for developing a common method for measuring the pasting properties for pulse flours. So in our preliminary test, we observed it's difficult to mix pulse flour with water to produce a smooth slurry before you do the testing. So in the so we did use so therefore we use the three mixing methods before loading the sample onto the RV instrument. So method one is to mix the sample with water with the metal spatula for 1 minute. The method two is mixed with 2 minutes. Three is just mix a small amount of pea flour and water at a time until all the material and the water were incorporated into the slurry. So yes, so now here is shows you the results with those three mixing methods. So So you can see the two colors. You can see the lines, two colors, orange and blue. So they represent for each curve represented the two determinations for a same sample. So we mix the flower, pea flower sample with, just give you an example with a pea flower sample with method 1, you can see the results in the large variation or standard deviations of those pasting characteristics, those including the like peak viscosity through or final viscosity, so those parameters. So when we use the method 2 or method 3, you can see they produce a repeatable, consistent, and similar results. So therefore, we in our study we select the method 2 for apply to rest of the study due to the less variation. We didn't select the method 3 because it takes a longer time compared to the 2 minutes mixing. Also, we look at the factors to see how the effect of the sample amount on the pasting characteristics to determine the appropriate amount of the samples used for the testing. So in the literature, there are various amounts of sample, different samples used in the literature. So this will be hard to compare the results. As from here, this is the results you can see from bottom to the top. The bottom is a weight of 3 gram, 3.5. Here, I think it's 4.1. So 4.5. So you can see, so as the amounts increasing, the amount increasing, so it will give you complete the characteristics of the pea flower. So from this study, we are recommended to use 4.5 gram for pulse flower, for pulse flowers. So here we tested a variety of pulse flowers, including peas, lentils, chickpeas, and faba and beans. Use the AACC methods 76-21-02 STD1. So as we noticed that, so from on the left of this curve, we noticed that incomplete the pasting curve for navy beans. So you can see here, cannot see clearly the characteristics. So we modified this AACC STD1 profile by extending the holding time. Here you can see here the shorter here. We extended the heating the holding time at 90 degrees for 2 minutes longer than the STD1 methods. So here are the results. So you can see a complete pasting profile for navy bean flower was obtained with this modification. So other conditions are the same. We only extended the holding time. So a longer holding time at 90 degrees provide a better measurement of the breakdown of the swollen starch granules in those flowers. So in the summary, so we the STD1 AACC STD1 methods. So it's a short. There are other methods available for the AACC one, but it's take longer. So our goal is to develop a faster methods. So that's why we select the STD1. So this profile was modified for application to all the different type of pulse flowers. So this including the weight amount, 4.5 gram is appropriate. Mixed for 2 minutes before load onto the RVA instrument, and extending the holding time for 2 minutes. So this shows you the all those different pulse flower, including peas, lentil, chickpeas, bean, green northern, I would mention, pinto, navy. So all those, the characteristics of those material use the modified methods. So you can see the methods, the modified methods can tell the difference in pasting characteristics for all those different pulse flowers. So yeah, now I'm going to move on to the determination of hardness of for the pulse seed. So the common procedures for measure hardness of pulse seeds are not readily available. So therefore, the objective of this study was to develop methods for measure hardness of pulse seeds with a texture analyzer. So this is a texture analyzer. So how we measure it is just load a single seed on this platform. So this is a cell for compress the seeds. So here is we showed this hard. So we determined this hardness, seed hardness, use a texture analyzer. So so how in our okay, let me see here. Sorry, a little bit more. So this is a typical compression curve for different pulse crops. On top of the graphs, you can see the chickpea and the yellow peas. You can see they have 2 peaks, where for kidney beans and green lentils, they all have 1 peak. So what happens is when a chickpea or yellow pea seeds was compressed, the seed was first cracked open, and those pieces of the materials immediately falling down out of the contact of the probe. That's why they first create first peak. And then the second peak was produced when the probe continues to press. So all this probe continues to press the broken pieces. So this is results in a second peak. So for kidney beans or green lentils, the cracked pieces in the compress tend to stay in contact with the probe where compression the seed. So this indicates that the compression behavior was different among the pulses. So in our study, we defined the hardness as the total work required to compress a single seed. We used the total work rather than the force to define the hardness was to reflect the effect of the seed size, because the pulses, you see, they have a different size. So for larger seed size, the probe needs to travel longer. distance to compress the seed. So what for if you have two peaks, so the hardness would be the area of this under this curve, A1 plus A2. If you only had one peak for that, so the hardness would be only for the under this area is the work the total work required for compress a seed. So we started the investigate the effect of compression rate on the hardness of pulses. So this graph shows the hardness of different pulse determined at a different compression rate. So results show you can see results shows that there's no significant effect of compression rate on the hardness of different pulses. So therefore, we just choose 1 millimeter per second in all the testing. So also we started to effect the percent strain, how much percentage you compress the hardness. So you can see here, just give you example, pea and the lentils. So increase percentage of strain generally increase the hardness of pulse seed. So we found that all the samples showed a significant difference in hardness at 70% of strain. So therefore, in our study, we select 70% of strain for all the rest of the test. Okay. Here, since the hardness was determined based on one seed, so how many seeds will be required to get give a representative value? So we determined that 10 seeds and 20 seeds. Results shows there is no significant difference for different pulses. You can see. So we decided to use a 10, determine 10 seeds, and then determine the average of the hardness. So here is the hardness of determined and the optimum condition. So at 1 millimeter per second, percent of the strain is 70%. So the result you can see indicated. You can see the differences, the hardness. So navy bean shows the hardest. Lentil has less hardness. Okay, thank you. So I would like to acknowledge the funding organizations for supporting this research, and thank you for your attention.
Thank you very much. We'll have time. We'll see you again here at the question and answer period. But I'd like to introduce our last speaker, Dr. Jim House, who will be presenting on in vitro methods of protein quality analysis. So take it away, Jim.
Great. Thanks, Janelle. And thanks, Pulse Canada, for inviting me to present here today. So as Janelle mentioned, I'm going to go through a little bit of background and then some methods that were currently being investigated for and consensus studies that are being looked at to validate in vitro methods for assessing protein quality. Just to put in a little bit of context, why we're interested in looking at protein quality. This is just one perspective, but from a nutritional standpoint. Here you're looking at Canada's Food Guide, which has been recently, within the last 3 years, introduced, where the focus has moved away from the discussions on meat and alternatives and dairy and alternatives to a category of protein foods. And so dietary guidance to recommend the consumption of protein foods, with the special statement made by Health Canada that we should be eating proteins that come from plants more often. And so that puts the onus on the consumer to understand what is a protein food, how to find protein foods within the marketplace, and in particular, plant-based protein sources. So how do we find plant-based proteins? Well, consumers are looking for them, but how do they find them? So certainly they can look at the nutrition facts table and get a sense of how much protein is in a serving. I've just given a couple of examples of chickpea products that are available, whole chickpea products that are available on the marketplace. But certainly the nutrition facts table only really tells you how much protein is in it. It doesn't really give you an assessment of the quality of the protein. So, and that's really where the concept of a protein content claim comes into effect. And that's really the ability to say that it's a good source of protein or an excellent source of protein on the label. Now, in North America, protein content claims must be substantiated. And in Canada and the US, in particular, we use protein quality, whereas other jurisdictions for substantiation of protein content claims use different approaches. And I've summarized this in this slide here. So the top two rows being USA and Canada, where we use both protein quality and quantity for establishing or substantiating protein content claims. And in particular, both of those methods are now more or less relying on the use of what's called the protein digestibility corrected amino acid score, or PDCAS. And in the US, there is a set target of PDCAS corrected protein that one has to have in a serving in order to qualify as either a good source or an excellent source. And those numbers are shown in that table. In Canada, we've used the system called the protein rating system, which values of between 20 and 39.9 would equal a good source. Essentially, it's a way of multiplying the protein efficiency ratio that's determined in a rat bioassay by the amount of protein within a serving size or a representative amount. And when you get those values, you can claim a good source or excellent source. The challenge there is that PER and PDCAS are different methods of assessment. Health Canada has just recently, within the last 3 years, allowed for the calculation of PER based on PDCAS values. And in a webinar just held last week, they again reiterated that they are going to be maintaining the use of PDCAS for the calculation of protein ratings. So this really puts the onus on the industry based in particular in North America, to understand the PDCAS method, some of the challenges and opportunities that exist with, because in other regions, primarily based on protein quantity. So the expression of either absolute amount of protein or relative to energy. So, but for the purposes of today, I'm going to be focusing on the estimation of protein quality and in essence using the PDCAS method. Now, the fundamentals of protein quality, essentially, when you're looking at protein quality, there are two components: the amino acid composition, or how well does that amino acid pattern match human amino acid needs. And then the second component is the digestibility or the availability of that protein. And then to what extent are the amino acids digested, absorbed, and ultimately made available for metabolic demands. Now, with the amino acid composition, we're typically looking to identify a pattern that meets or exceeds the reference pattern of human amino acid requirement. If it does, then the resulting amino acid score would be greater than 1, because all of the amino acids would be present at higher amounts relative to human amino acid needs for a given life stage. What we find, though, in particular with plant and alternative-based proteins, is that there's typically one amino acid or two amino acids that might be limiting or co-limiting. In the case of pulses, it's typically tryptophan or the sulfur amino acids methionine and cysteine that tend to be limiting. Whereas in cereals, it tends to be limiting in lysine. And so a typical practice for overcoming these limitations is to create blends of pulses and cereals. It's been done for generations globally in dietary patterns, mixing, say, beans and rice or other pulse cereal combinations. Now, when it comes to digestibility, the plant-based proteins are also typically present with lower digestibility, and it's really a function of the extent that they've been processed. So if you have a plant-based source and it's just been milled, you are reducing the particle size and you're removing some of the encapsulating effect of the cell wall, but you really haven't broken up that cell to release the proteins. So there could be the encapsulating effect of the cell wall or the presence of protease inhibitors. You can increase the digestibility of proteins by further concentrating or isolating it, or in other words, removing those factors that are known to limit digestibility. And so isolation, the development of protein isolates is one way to do that. Now, the PDCAS method that we currently use in North America, as I mentioned, is a product of the amino acid score, which is the amino acid in food and relative to the reference pattern. There's a couple of things that we need to keep in mind, is that this is defined in the regulations based on the methodology that should be used, in particular the reference pattern. And the current requirement for determining the amino acid score for PDCAS calculations is to use the reference pattern of 2 to 5-year-old school children, and that was based on the FAO 1991 report. That remains in the guidelines for both Canada and the US. There are other reports that have been published much more recently that are recommending alternative patterns, but it's really important that stakeholders acknowledge and recognize that when it comes to substantiating protein quality in foods, that the reference pattern that is legally required is the reference pattern for 2 to 5-year-old school children from 1991. And that's for foods for non-infant or sole sources of nutrition. So for example, pulses. So that's the one component of the amino acid score. The other component, and this again is important to understand, is the measurement of true fecal protein digestibility is the required method in both the Code of Federal Regulations for U.S. Food and Drug and the recognized approach that Health Canada has allowed industry to use for determining PDCAS. And so that methodology is a rodent bioassay, and you basically are measuring nitrogen in and nitrogen out. And so, again, it's important to recognize is that legally, you have to use the true fecal protein digestibility that's determined in an official rodent bioassay. So this creates challenges, and that's something that we need to keep in mind, because we know that there are a number of factors that impact the ability to make protein content claims. And in particular, up at the top, you can see the multiple sources of variability: crop variety, genetics, agronomic practices, environmental factors, processing, as I mentioned, in terms of creating concentrates or isolates, and also the analytical methods. All of these represent a source of variability. And if you're going to be able to understand that, how variability impacts protein quality or the ability to make protein content claims, you need methods that are robust, but also that are practical. And for all intents and purposes, the use of a rodent bioassay is not practical for determining the digestibility and the multiple sources of variability that exist. There are other components that influence the ability to make protein content claims, but these, as I mentioned, are defined by the regulators within specific jurisdictions. But let's turn our attention to the challenges with current methods for measuring digestibility for claims. So as I mentioned, the current methods, both the protein efficiency ratio, which is really just a growth assay, it's more or less being, because Health Canada now allows the use of PDCAS, it's less and less likely that you're going to see PER being measured for determining protein quality for Canadian purposes. They'll use PDCAS because then that value can be used in both Canada and the US. But the current methods, as well as the proposed DIAS methods, that's the digestible indispensable amino acid score method. Essentially, it's the same principle as the PDCAS, but it treats the amino acid as the nutrient and not the protein. And so you're looking at individual amino acid digestibility. But all of these methods rely on animal models. So rodent for PDCAS, swine or rodent for the DIAS when human data is not available. This does create challenges for the protein sector when data is not available for new or alternative proteins. And in particular, in vivo methods are not practical to measure sources of variability, those sources of variability that exist when you're looking at influences on either the amino acid composition or on the digestibility. For the purposes of today, I'm not going to talk about variability and the requirements for substantiating or validating methods associated with amino acid determination. That's a whole other component and requires further attention. But I'll be focusing primarily on alternative approaches to measure digestibility, in particular for protein content claim substantiation. So one of the biggest challenges is that for the alternative protein sector in particular is that consumer packaged good companies are seeking vegan certification on products, and they're demanding that ingredients have not undergone animal testing. So I've given you one example here, the certified vegan. Actually, within their their policies that have been published more recently, they're reluctantly allowing the use of PDCAS and an animal model to go forward with certified vegan symbols, because they recognize that industry doesn't have a choice because it's the law of the land, and they don't want to limit the ability to continue to advance the alternative protein sector. So they are reluctantly allowing, but I think we need to recognize that we are in an era of reduced animal usage for regulatory testing. We're seeing it already coming into the US and Canada for cosmetic testing and banning of the use of animals for other regulatory purposes. It won't be long before we see similar pressure being brought to bear to reduce animal usage for protein content claims, because it's the only protein's the only nutrient that requires an animal test for determining for substantiating a protein quality or protein or nutrient content claim. But it is required a major hurdle. So now we need to really ask ourselves, what are the other options? So we've recently published a paper. It should be coming out within the next week in pre-press form that looked at alternatives to animal models, where we could either focus on quantity alone, which is what's been used in other jurisdictions. I don't think this is going to serve the sector well in the long run, because there are new proteins that are coming onto the marketplace, and it is important that we have some understanding of the ability of those proteins to contribute to the protein needs of the consumer. So one way to do that is just focusing on the amino acid score only, without a correction for digestibility. Or we could use the amino acid score in conjunction with a fixed digestibility coefficient. Say everybody uses 0.8 as a digestibility coefficient. That would require consensus across the sector to say that we're going to establish a digestibility coefficient for all proteins at 0.8 or 0.85. I think there would be a lot of debate as to what that coefficient would be. But I think a more pragmatic approach is to look at in vitro methods, where there has been substantial investment of time and effort to look at alternatives to the use of animals. So that's going to be the focus of the rest of this talk, is to look at in vitro approaches, some of the advantages and disadvantages. And so certainly from an advantages standpoint, it does remove most of the ethical concerns of animal testing. It's simple, economical, and readily implemented. We have the ability to use robust amino acid data sets. Both the Canadian Nutrient File and Food Data Central publish amino acid values for a whole host of food sources within their data sets. And so you have access, and you also have access to robust laboratory assessment through a number of different labs that can measure amino acids. Another nice thing about this approach is that it's additive. It does allow you to calculate the PDCAS or ultimately the DIAS of mixtures. And so you don't need to measure final products all the time. You can actually do some product formulations on the basis of understanding your ingredient, the values for your individual ingredients. And it does maintain a process for regulatory oversight of novel protein. But some of the key disadvantages is that it requires additional validation against in vivo measures, and that there's a need for standardized approaches and interlaboratory validation. And that's really going to be at the heart of this presentation. So for the purposes of today, there are many model systems available. They vary in complexity from simple static methods, which basically means that it's sort of like a one-pot assessment, where your sample and enzymes go into a single chamber. You allow the protein to be digested, and then you measure the end product of digestion. So that's a fairly simple, what's called a static method. You also have more complex dynamic models. And so there are a number of what we call simulated gastrointestinal tracts that are computer controlled. They allow you to adjust pH, temperature, and maintain and control peristalsis. These are much more complex, but also very costly methods. And so I think we need to be mindful of that they may not also be pragmatic in terms of measuring the variability across the alternative or plant protein space. So for the purposes of today, I'm going to focus on three, well, technically four different methods that are currently being evaluated for use within the food sector. One is called the ASAP quality score method. The other one is either the pH drop or the pH stat method. And then finally, the InfoGest 2.0 methodologies. And so some of the key considerations for these methods are: what is their validation status? How accurate are they? And are they fit for purpose? So do they really, when we're looking at content claim substantiation, we're really just trying to get an assessment of the relative availability of nutrients so that consumers can make comparisons. And so is the method fit for purpose? It may not necessarily be completely accurate in relation to the digestibility conditions within a human setting, but if it provides relative information, I think that there's an argument to be made that that's sufficient for content claim substantiation in particular. And then that little diagram on the right, it's we always want things fast, cheap, and good. Choose two. So that's the old adage there. And so I think we need to keep that in mind. So let's look at the ASAP method. So this is a method that is being, it was developed first at the Medallion Labs. It's now being sold as a kit from Megazyme. And essentially, it's a static-based method where the proteins are digested through the use of pepsin and then trypsin and chymotrypsin. So you have both the gastric and an intestinal phase. And then you measure the amino acids that are being produced. And so Megazyme and Medallion have established the protocols, and the graphs on the left is provided by the companies to show you both the correlation of the digestibility scores with in vivo scores. And so based on this data, you can see that there's very good approximation or estimation of digestibility and the results into PDCAS, which is the bottom left curve. And so this method is currently undergoing ring trial validation. It has been used in publications to measure, for example, here's a graphic to show you the protein quality of seaweed. And the blue bars represent the in vitro protein digestibility determined with the ASAP method. And you can see they're all very similar, roughly around 0.8. And that ultimately the PDCAS that results, which is the red bars, that's when you multiply the digestibility by the amino acid score. So the biggest factor that's influencing the quality of the seaweeds is really the amino acid pattern of the seaweeds, because the digestibility coefficients are all very similar. But it can be used. Again, this is not an approved method. None of the in vitro methods are approved by Health Canada or the FDA for protein content claim substantiation, but it can be used for product formulation and also to get an understanding of the relative impact of processing or what have you on protein quality. Another approach that's being looked at are, again, simple static methods. These are methods that were cited in the FAO 1991 report. One is called the pH drop method. One is the pH stat method. They're both conceptually similar in that you take a test protein, it's pre-treated to produce a material of a particular particle size, and then it undergoes static enzymatic digestion. And then you either measure the drop in pH over a set time period, which is a reflection of the release of acidic amino acids, or you measure the amount of base that's required to maintain pH at a constant level. And both of these approaches can be used to determine protein digestibility. So here's some samples. This is from our lab looking at plant protein blends, buckwheat and pinto bean. And you can see that In vitro protein digestibility, you get reasonable approximation of, and this is just for a few blends. This is buckwheat and pinto bean. And when you look at the PD-Cas, resulting PD-Cas, you get an R squared of 0.92. So these methods are well established, but they have not yet been validated. And so that's really the protocol that through funding from IFINS, which is the Institute for the Advancement of Food and Nutritional Sciences, we are looking at doing a ring study to look at the pH drop and the pH stat method. And the collaborative study is really, you can link to it here. If you take a shot of that QR code, you can go into the method that it's in the Center for Open Science and look at the validation protocol that we've established to have AOCS, the American Association of American Oil Chemist Society, that is going to do the method assessment, and as we've developed this collaborative study. Currently, we have the methods approved through the AOCS committees. We have 8 participating labs, and we're working with 12 protein samples, animal and plant, isolates and flours. And we are going to be providing that data to AOCS, and then they will be doing the statistical assessment and validation for these protocols. Finally, I'll turn attention to the last example that I'll be providing today, which is the InfAGEST protocol. Now, the InfAGEST is an international consortium based in Europe that was established to standardize in vitro conditions. And there's been a number of publications, but the one that is most recently published is in 2019 by Broadcorp et al. And this InfAGEST protocol standardizes the activity of the enzymes. It standardizes the digestion conditions. But InfAGEST by itself is really just the digestion. It doesn't really work to tell you about what's happening to protein or to amino acids. It's really establishing the conditions for in vitro digestions. There was further work that was needed to help validate this method for determination of amino acid score. And so in particular, DIAS and PD-Cas. And so there's been recent publications for meat and plant-based burgers and dairy products. And essentially this method, as you can see, this is the graphics just showing you that all the steps that you can go through. But the details are in the Nature Protocols paper from 2019, and you can refer to that. More recently, this paper that was published in 2023 by Souza et al. Provides the conditions for measuring digestibility of amino acids and protein, which is more relevant for today's conditions. So it's only been very, very recently. And we've actually been collaborating with the group that's been spearheading this two major ring trials. And you can see some of the data here is that here's the total digestibility that can be used to measure PD-Cas. So here's a soy-based burger, a pea fava-based burger, and a meat, and this is raw versus grilled. And showing you that for soy and pea fava, there's a reduction with grilling, whereas the meat burger doesn't really see much reduction in digestibility. So with the InfAGEST protocol, there's 2 ring trials that have been completed and are in preparation for publication. So the dairy-focused one, and then there's a plant and animal-based foods one. And with collaboration from our lab, we're working with the primary group that's working on this method, and we measured with funding from Pulse Canada and Protein Industries Canada, we've measured the DIAS on 20 foods, and we've also had inserted the inclusion of protein concentrates and isolates into a major ring trial that's happening across Europe. And so we're also involved in that. And just one final thing is that because this InfAGEST protocol is somewhat involved, we'll be hosting an InfAGEST training school in 2024. So I think look for more details on that. So moving forward, protein is the only nutrient that requires an animal bioassay for nutrient content claim substantiation. There are alternatives that are needed, and in vitro methods offer a compromise for understanding the impact of various factors on digestive processes. And then until or if Health Canada FDA move away from PD-Cas, we need to continue to promote acceptance of in vitro methods for estimating the digestibility for content claims. So we need alternative approaches to animal models. We need validation for the alternative approaches, and the methods need to reflect the complexity of the protein food system. So with that, I just like make these acknowledgements, and for more information, you can flash on that QR code or email me if you'd like more information on any of the information that we presented today. So with that, I'll say thank you very much, and I'll turn it over to Janelle.
Great, thank you very much. So we will now have some time for questions here. I see a couple rolling in already. So just a reminder, you can type them in using the chat function, which is located on the right-hand side of your screen. So I see the first question that we have is for Dr. Nickerson. If you can just comment on the potential loss of material or destruction of some of the foams that might occur as a result of transferring that material from the beaker to the graduated cylinder. That's the first kind of comment. And then the second is just if you can maybe touch on, there's a reference to a sparging method as well, if you're able to comment on how that might relate to the method that you presented on here today.
Okay, so yeah, you do. You do see a loss when you do it in a beaker and you transfer it over to the graduated cylinder. There is an inherent loss. We use a spatula to sort of get the remnants from the beaker into the thing, and but there's no sort of better way to do that for that particular test. And typically you get better the more practice you do at doing the test. You get more consistent and things like that with that. So you don't get, you do lose, but not a huge amount. And yeah, sometimes I'm just reading that thing that you don't have a defined foam line in the graduated cylinder. And again, that's practice, sort of estimating it. And it is a broad estimate because you're sort of doing a visual representation of where the meniscus is on the foam, and depending on the morphology of foam, it may not be that clear, right? So it's just about practice, and there's inherent visibility. We are using that more advanced technique it's based on light scattering to determine a more a better estimation, but that's quite an expensive machine. So there's flaws to the technique for sure. And sparging, can be used to do that as well. So some people have created a system which they sparge gas right into the graduated cylinder or vessel and can measure the foam volume there. So there is no transfer. I find the sparging not as strong as the mechanical shear, but it is used in different product applications as well.
Great, thank you. The next question is kind of an open question to all speakers here today, is just if you can comment on the need for the sector to work towards open source methods or standards. So I don't know if anyone wants to take a stab at that.
Sure, I'll go. Open source, I think the more that the industry can move to standardized methods, so we can compare across labs and really understand companies' technical spec sheets and things like that. I think the better. The more open source methods available, I think will only benefit the industry as it grows, to support that.
Yeah, I think it's a really good question, because certainly when you start looking at the accrediting bodies that are currently investing a significant amount of time for methods standardization, I think there's an incentive on their part to try to recoup some of those costs by selling the methods. And so it's that balance. And so if you're going to go to open source, there needs to be sort of a change in the approach, and so there need to be commitment from the sector that the review, the technical reviews will be done sort of in sort of a traditional peer-reviewed process. And so I think it's doable, but there's a lot of effort. Just having gone through a couple of these, there's a lot of effort and materials that are involved, and in terms of going through an official accreditation process. And so it does put a little bit more onus back onto those that are seeking to use those methods to identify the true opportunities there.
Okay. I think I kind of agree with Mike and Jim what it said. Yeah, open sources could provide, So the thing is, it just need to be whatever the methods, the open sources need to be verified, and the conditions, whatever, they need to be specified clearly, so that other lab, when they use it, it can to repeat or their test. So I think I think that's what I would say. Yeah, Daishin. Yeah.
Thank you all. The next question that we have here is for Dr. Wang. So regarding the pasting method that you presented, if you can comment on how that might compare to using the high temperature profile method of the RVA, then rather than just extending that holding time there.
Okay, thank you. That's a good question. So currently we in our lab, we don't have that capacity measure very higher temperature over 100 degree. That's a profile. We didn't try that, so I'm not sure. So how that's going to compare with the one we're using. For just in terms of the methods we're using, it's only extended about 2 minutes, so it's not that long. So the total running time is 15 minutes. So that's really can apply to all those pulse crops we tested in lab. So it give you very good complete profile. So yeah, that's I could see. So, and also it's compared to the high temperature ones, the current method we use more cost effective. So yeah, that's how I can comment on that.
Perfect, thank you. The next question we have here is also for Ning. So just looking at the data you presented for the oil absorption capacity, there were lower values compared to the other method. And just a comment that may be due to centrifugal forces. And if you have any other thoughts on that, I'm not sure if you're able to read that comment specifically yourself.
Okay, so we did study the effect of centrifuge force on the final value. So because here what we determine is oil absorption capacity, so we try to remove the free oil. So when you use the conventional methods, so like I mentioned in my presentation, you have depends on material, what type of material. Some material they may absorb the oil after centrifugation. That you can see when you determine it. So there's some oil go back to the matrix. So that's why you get a higher value. And also some, so yes, the centrifuge force, the one we use is determined to the point where give you a consistent value. So which means all the free oil were removed. So that's, you can see that's compared conventional methods, all the free oil were removed. So that's why I think you produce a lower value for the new methods as compared to the conventional method. Yeah.
Thank you. All right, our next question here is for Jim. So just a comment that from the industry that there also might be some challenges in terms of measuring amino acids, and you referenced that during your presentation as well. Just if you can comment on any opportunities there for more cost-effective techniques to evaluate amino acids.
Yeah, that's a great question. Thanks, Janelle, and thanks, Julianne, for asking the question. Essentially, the challenge with measuring amino acids is that in order to get the full spectrum of the amino acids, which includes the sulfur amino acids and tryptophan, in addition to all of the other ones, you have to do 3 separate hydrolysates because of the challenges with the stability of the sulfur amino acids. They have their own unique qualities, and so you have to do a separate oxidation step for those. And then tryptophan it degrades under the standard alkali or acidic hydrolysis conditions that we use for all of the other amino acids, and so you have to use a separate alkaline hydrolysis section. So in order to measure the amino acids, you have to break up that protein. And so that's one of the biggest challenges, is just the number of hydrolysates that you have to do. There are advances that are happening with the technologies, chromatography technologies, and other technologies that can make it more rapid and perhaps more sensitive. But again, these would need to be standardized, because the existing methods, I think there's a need, just as we mentioned for digestibility, there's a need for validation and standardization. So that's one of the biggest challenges, is just the amount, the number of steps that one needs to take, and because it's time intensive, labor intensive, and resource intensive. Now, one of the approaches that we are using that can potentially help the sector is maybe not for all foods, but it's something that we're working on for individual crops, is the use of NIR to very quickly determine the amino acid composition. And you can do that by establishing calibration curves. And we've currently done that for lentils, peas, soybeans, canola. We're working on one for sunflower seeds at the present time. And you can actually predict the amino acid composition if you have a reference wet chemistry values to support that. Now, the one challenge is that while NIR, traditional NIR, works well for like macronutrients, those that are in the percentage range. Amino acids are at that range, but some of them are lower. And so you get a little bit more challenging when you're measuring, when you want to accurately measure amino acids that tend to be lower, which typically are the ones you're interested in. Like if you're a breeder and you want to breed for enhanced protein quality in peas or lentils, it's typically the tryptophan or sulfurs that you're interested in. And those are the ones that tend to give us a little lower R squared on the calibration curves. And so we're looking at alternative approaches using spectroscopy-based techniques in order to do that. And so there's some interesting work happening there in our lab and other places to try to come up with some of those methods.
Okay, thank you. I guess a follow-up question to that. I know you mentioned that you do see a potential in the future to move away from animal-based testing methods for substantiating protein content claims. Do you maybe have a guess as to what that timeline might look like, just in your perspective? I'm just
Where's
curious.
my crystal ball?
Yeah, I know.
Judging by, I was on a webinar last week with Health Canada, and they referenced a workshop that was held in 2016 that made a recommendation for the changes that needed to be made, and that they last week only introduced a small percentage of that. It tends to move at glacial speed, and I think we can all appreciate that there's lots of interest or lots of other things that are occupying the minds of regulators right now. And I think they're seeing a system that, it works. There's clearly challenges, but we're doing our part, and others are doing their part by positioning validated methods to help support a shift in regulatory reform. And so, it would be very hard to predict timelines when it comes to policy, because a lot of these have to be introduced, especially in the U.S. through regulatory processes. At least the nice thing that's happening in Canada right now is that they've moved to they made some changes that's going to be coming forward this fall. That's going to basically strip a lot of the specifics out of the regulations for measuring protein quality. And they're going to be using what's called incorporation by reference. And so that the actual regulation will be very, very thin, like it won't have very many details, but it'll refer to a particular document that can be updated much more frequently. And so that regulatory reform will speed things up, but they have to get that established first. And so I was really heartened to see that that's happening and will be coming forward this fall.
That's great. Thank you, Jim. So it looks like we're at time here. So big thanks to all of our speakers here today. It's very informative. And this is a particular challenge for the pulse sector. So really appreciate your time here today. For those of you on the webinar, thank you for joining us. Just as a reminder, it'd be very helpful to get your insights from that survey. You should be able to find that in a link below. And we will be circulating the recording for this webinar following today. So thank you so much. And please feel free to reach out with any questions moving forward. So wishing everyone a great day, and thanks.